This is the first of 4 lectures on algebra. In this particular lecture, we're going to look at the development of algebraic symbology. We're going to look at how algebra really is a generalization of arithmetic. And we're going to see how using algebra can help us understand certain tricks or magic kind of things we do with arithmetic. But first, we must understand that the key to understanding algebra is knowing what a variable is. A variable is simply a symbol that stands for some value that can vary, or some unknown number. And in many cases, if it's an unknown number, the variable can stand for any number, but only one or two of those possible values will actually satisfy the situation we're looking at. A perusal of elementary school mathematics texts will show that variables are introduced early in the education process. It doesn't start in algebra in high school. For example, you might see a problem such as 5 plus blue square equals 8, where the student is learning about the missing addend. Or possibly 10 minus red triangle equals 7. And again, brightly colored geometric shapes are used to make it pleasant for the young child. But in actuality, what they're looking at is 5 plus some unknown quantity is 8. That unknown quantity is 3. It could be 4, but of course 5 plus 4 is not 8. So the blue square is a variable. In the second problem, 10 minus red triangle, that red triangle is a variable. It could be any number, but only one number, which happens to be 3, will make it work. Typically, letters of the alphabet are used as variables. Usually, in fact, X, Y, and Z, the last 3 letters are used because they don't appear quite as much as some other letters in our everyday use. Actually, any symbol could be used for a variable other than, obviously, the numerals or symbols for operation like plus and minus and divide and such. In fact, when algebra became very popular, people struggled with the symbol for multiplication. Since multiplication symbol was an X, and X was now a favorite letter to be used as a variable, and what happened eventually, they started using dots, and on most calculators today, if you have a graphing calculator, when you punch the multiplication button, you get a little asterisk, or I call it snowflake, which stands for multiplication. So that's the one difficulty. Otherwise, you could use any symbol you want. The reason that letters are used is that they're commonly recognized and easy to write. Using complex symbols will make it very difficult to recognize and, for some people, impossible to write. In early mathematical writings, and it was previously mentioned, that words were used, and eventually abbreviations were used to stand for mathematical information. And fairly early on, in fact, in the 4th century AD, there was a bare beginning of using symbols, single symbols or sets of symbols that were not simply abbreviations as such, to represent some mathematical computation. For example, in early Greek writing in the 4th century AD, we see the symbol, it's a kappa, looks like a K, with a superscript, right, almost like raised to a power, of the letter nu. And this represented the Greek word kubos, which we would translate as cubic. So in dealing with a cubic situation, this symbol was used. It was not very common, but then again, there wasn't a whole lot of writing on algebraic things back in the 4th century AD. Also, a 4th century Greek mathematician used a symbol that sort of looked like the tines of a trident pointed down with the Greek letter delta, and again, the superscript nu. And this stood for the negative square of a number. I'm not sure why, but it did. And again, I'm just basing that on translations of the writings of these early Greek mathematicians. The more general use of polynomials began in the 16th century, and eventually, over a period of quite a few decades, led to the notation we use today. A polynomial, which is the founding element of algebra, a polynomial is the sum of one or more terms, with each term having a real number multiplied by a variable, which is then raised to a whole number power. So, for example, 3x to the 4th would be a monomial. 3x to the 4th plus 2 would be a polynomial with two monomials, 3x to the fourth and 2. So that each term of that polynomial is called a monomial, mono being 1. A polynomial with two terms is called a binomial. 3 terms, a trinomial, but in general, they're all polynomials. A monomial can be a number. I mean, 3 is a monomial. It could be a fraction, 1/2. It could be a negative number, negative 2.1. It could even be a square root, a rational number, but it must be real. The power of the variable must be a whole number. Obviously, the power of the variable is 0. X to the 0 is 1. But otherwise, we could have negative y, we could have z to the second, and obviously terms such as 5x or negative 3z squared would be monomials. The degree of a polynomial is the highest power of any monomial in that polynomial. So if we looked at x to the third minus 14x squared plus 7x minus 100, one would say, what is the highest power in that polynomial? And the answer would be 3. The x to the third is the monomial term with the highest power. That polynomial has degree 3. The coefficients are the numbers in front of each of the monomials. So in the x to the third minus 14x squared plus 7x minus 100, the coefficients would be 1 for 1x to the third, negative 14 for minus 14x squared, plus 7 for plus 7x, and of course the negative 100 would be a coefficient or the constant term. The lead coefficient would be the coefficient of the highest power term. So in the polynomial we've been talking about, the lead coefficient would be 1, since the number in front of the x to the third is 1. We will focus on polynomials with only one variable. Obviously, in many algebra texts, you will find polynomials that have x's and y's and a's and b's floating around. We're going to strictly speak of polynomials with one variable, the variable x. And we're going to focus on that because that will show us how polynomials help us understand that algebra is truly a generalization of arithmetic. In the 16th century, scholars struggled to adapt a universal system, that is a system accepted by all scientists and mathematicians, for writing variable expressions. In 1557, the equal sign that we know today, the two parallel horizontal line segments, was first used. And in fact, it was much longer in its use than it is today. But that was the very first use, 1557. In 1591, Francois Viet wrote a polynomial equation as Roman numeral 1 QC minus 15 QQ plus 85C minus 225Q plus 274N equator 120. He was writing an equation. Could you imagine if you had to write equations like that? If we wanted to translate Viet's equation in today's symbology, it would be x to the sixth, the Roman numeral 1 standing for a lead coefficient of 1, the QC representing the sixth power, minus 15x to the fourth, plus 85x to the third, minus 225x to the second, plus 274x equals 120. By 1637, René Descartes, and I said I will mention Descartes quite a bit, one of the great mathematicians who led us into modern mathematics, was writing an equation such as x to the third minus 6xx plus 13x minus 10. Isaac Newton established that the second power of x should be written as x to the second rather than xx. And Newton, of course, was also in the latter part of the 17th century. It is best as if polynomials were looked at as whole numbers whose place values are the powers of x, powers of the variable, as opposed to powers of 10. In whole numbers, our place values are powers of 10. For example, we could look at the whole number 237. 237 is a simple number, but if we looked at the polynomial 2x squared plus 3x plus 7, in my mind, they are the same. In fact, if you allow x to be 10, 2x squared plus 3x plus 7 is indeed 237. But in our writing of whole numbers, we're restricted to using only one of the 10 digits for each place value, and it had to be positive. We couldn't write a number such as 200-37, where the number in the tens place was a -3. But in polynomials, we could. We could write 2x squared minus 3x plus 7. In fact, again, that would be equivalent to 200-37 if x was 10. So what is 200-37 mean? Well, 2 100s, -3 tens, and 7 ones would give us 177. So, you know, there's no real problem there except that we do not write whole numbers that way. We could, but it would be confusing. But we do write polynomials that way because it allows us to use various kinds of numbers as coefficients. We can write a polynomial, 2x squared plus a half x plus 7, because we can use a rational number as a coefficient. Consider the whole number 257. Now, people generally laugh when I say 257. But if we put a 3 in the tens place, it's 30. A 7 in the tens place is 70. So a half in the tens place would be halfty. And of course, again, the 2x squared plus a half x plus 7 would be equal to 257 if x was 10. But what is 257? Well, 2 hundreds. Half of 10 is 5, and 7 ones is 212. There is no need for zeros as placeholders when you're writing a polynomial because the place value is shown. If desired, we can write 2x to the third plus 25x plus 12. There's no need for an x squared term because there isn't any. If you wanted to put in plus 0x squared, you could, but it's not necessary. The methods for adding, subtracting, multiplying, and dividing polynomials make a great deal of sense when one realizes that they are exactly the same as how we add, subtract, multiply, and divide whole numbers. So let's take a look at these 4 operations and see how they relate. To add 2 or more polynomials, align the place values, which are the powers of x, and add the coefficients. Not very difficult. And therefore, we could see that 2x squared plus 3x plus 7 added to 3x squared minus 9x minus 1 would be easy to do. All we got to do is add up the x squareds, add up the x's, add up the numbers, the constants. And we'll get 5x squared minus 6x, because a positive 3x and a minus 9x is minus 6x, plus 6. And we can check this using our knowledge that if x is 10, it should be able to work. In fact, any value of x will work, but x is 10 is easy because 5x squared minus 6x, that's 500 minus 60, is 440, plus 6 is 446. And indeed, if you replace the x with 10 in each of the 2 polynomials we added, we get 237 plus 209, and indeed, that equals 446. So we've checked our answer. Subtracting polynomials, no different. Again, we can change all the signs in the second polynomial and add. Our rule for subtracting integers was change the sign. Here we have a sign for each monomial term, so we change all the signs in the second polynomial, the one we are subtracting. And therefore, 2x squared plus 3x plus 7 minus x squared plus 7x minus 8 can be rewritten as the first polynomial as it is, but then plus negative x squared minus 7x plus 8. We changed all the signs in the second polynomial. Now we add, and we get x to the second minus 4x plus 15. And again, we could check by replacing the x with 10, and we get 237 minus 162 equals 75. And indeed, x squared, 100, minus 4x minus 40 is 60, plus 15 equals 75. We know our answer is correct. Multiplication of polynomials is accomplished using the same techniques as we use in multiplying multi-digit whole numbers. Each monomial in a polynomial is multiplied by each monomial in the other polynomial. Watching our signs and remembering multiply digit times digit and place value times place value, but now our place values are powers of x. As with adding and subtracting, we can check our answers replacing x with 10. If indeed you say, you know, I don't believe that, or I'd like to check up on my knowledge of multiplying polynomials. Well, I would suggest that you take a look at the teaching company's tape series, either Algebra 1 or Algebra 2. Both talk about multiplying polynomials, and we don't have time right here to go through that, but I just thought I'd mention it in terms of relating the algebra to the arithmetic. In division, there are two ways we can divide polynomials, and we will restrict ourselves to simply dividing by a binomial, of a binomial of the form x plus or minus a number, where the number is a positive integer. Okay? And the reason for doing that is that we just want to just simply relate, again, the division of polynomials to the division of whole numbers in arithmetic. And again, dividing of polynomials beyond that is not that vital unless you happen to be an Algebra 2 teacher. We start with the highest powered term, and we divide by x. So we have x plus 2 divided into x squared minus 3x plus 7. And we divide the x into the x squared, and we divide, and we multiply, and we subtract, and we bring down, just as we did in 4th or 5th grade with long division. And we wind up with an answer of x minus 5 and a remainder of 17, which, of course, that answer can be written as x minus 5 plus 17 over x plus 2. That is, writing the remainder as a fraction, the remainder over the divisor. Well, someone probably some years, hundreds of years ago, was sitting around saying, this is too confusing. This is too much writing. I'm tired of writing all these terms. Let's find an easier way to do that. And the easier way, indeed, was a process called synthetic division. Now, synthetic division really is a simplified means of dividing a binomial of the form x plus or minus a into a polynomial. Briefly, the symbology is that you change, if you're dividing by x plus 2, you change the plus 2 to negative 2, and that is your divisor. And the process, so if we were dividing x plus 2 into x squared minus 3x plus 7, all we would write down is the change number, the negative 2, and then the coefficients of the three terms, 1, negative 3, and 7. And the process is simply you bring down the first number, you multiply, and keep adding. And eventually we get the same answer. We get x minus 5 with a remainder of 17. And again, if this is a refresher of something, you say, oh, I remember learning that, but I was confused by it, or why does it really work? Again, I would take a look at the Algebra 2 tape, and in that particular tape, I do a whole discussion of why that works and how it works. But in reality, dividing polynomials is not a vital skill. To me, the important thing is that when dealing with polynomials, we are really dealing with generalized whole numbers. The processes are the same. Adding, subtracting, multiplying, dividing have not changed from our first usage of those operations with whole numbers. What I'd like to do now is to take a look at a few sort of magic tricks that people are amazed by. Wow, this is exciting. You must be a superhuman person to understand how to do this. And in reality, there's no magic, just mathematics, and it doesn't take an elite person to understand it. And in fact, algebra allows us to see why it works. The first problem, which is sometimes called a trick, is called the birthday magic trick. You start with your birth month, 1 for January, 2 for February, etc., and multiply that number by 4. Get the answer. Add 16. Take that sum and multiply it by 5. Okay. Product of that answer is then subtracted. You subtract from that answer a 7. So it's the answer to the previous minus 7. You get that answer and multiply it by 5. Then add the day of the month in which you were born. So if it was the 5th of the month, you'd add 5. If you were born on the 31st, you'd add 31. And finally, you subtract 365. And you get your birthday. It's magic. And people are amazed. Oh, you got to have a master's degree in mathematics to be able to do this. Nonsense. But let's take an example first. Let's say your birthday was October 23rd. That is 1023. The first thing we would do is we would multiply the month 10 by 4, which would give us 40. The process requires us then to add 16. 40 plus 16 is 56. We multiply the 56 times 5, and this gives us 280. Okay? 280 minus 7 is 273. Multiplied by 5 gives us 1,365, to which we add 23, because this person was born October 23rd, so the day of the month was 23. That gives us 1,388. We subtract 365, and voila, we have 1,023, or 1023, which was this person's birthday. Well, that's magic. Is it magic? Of course not. And algebra will simply show us why it's not magic. Let's use variables m for the number of the month. So in that particular case, m would have been 10. And let us use d, symbol d, for the day of the month. In that particular situation, it was 23. And the answer we should get, obviously, is going to be the month and the day of the person's birth. Let's see why that works. Let's call our answer A. And we have an algebraic formula. And this formula simply allows us to do everything that the trick asked us to do, but in one equation. Since the first thing we're going to do is multiply by 4, the month by 4, we have 4m, and then we add 16, and that is in parentheses to be multiplied by 5, and then we subtract 7. And that whole part of the problem, that whole statement, is within square brackets, because then we're going to multiply it by 5. We're going to then add d and subtract 365. So what we have is 5, bracket 5, open parentheses, 4m plus 16, close parentheses, minus 7, close bracket, plus d, minus 365. Now, to an Algebra 1 student, that may be a challenging problem manipulating those symbols. But in reality, it's rather simple, because we wind up with 100m plus 365 plus d minus 365. And you can already see why we're going to subtract 365, because what that simply does is cancels out the plus 365. And we're left with 100m plus d. So if m had been 10, and d had been 23, 100m plus d would simply be 1,023. A few more examples. If m was 1 and d was 15, that is, the person was born on January 15th, the answer, 100m plus d, would be 115, since 1 times 100 is 100, and 15 added to 100 is 115, and 115 is January 15th. If the person was born on November 18th, you might know someone who was born on that particular day. November 18th would be 11m, and d is 18. Well, 100m plus d would be 11 times 100, which is 1,100, plus 18, 1,118, which is November 18th. There is no magic. It's just the use of mathematics. Now, tell you the truth, I love playing with mathematics. I don't think I would have taken the time to figure out what that trick involved, but someone did, and it demonstrates that we can take a situation, an algebraic situation, and then use it in any arithmetic situation, since algebra is the generalization of arithmetic. I'd like to go back to Lecture 3. And in Lecture 3, we looked at a cycle of 5 fractions. We started out with 2 numbers, 2 fractions, and we then took the second number, added 1, and divided by the first number, and that became our third number in the sequence. We then took that third number, added 1, and divided by the second number in the sequence. We then took that fourth number, added 1, and divided by the third number in the sequence, and that became the fifth number. And then finally, we took the fifth number, and we added 1 and divided by the fourth number in the sequence, and we wound up with the first number. So we had this cycle. Why? It was amazing. But it works very simply when you look at the algebra. Quite frankly, the algebra is not very simple looking. And I wouldn't recommend it unless someone was really had nothing better to do. In fact, I recommend to my students, my students that are young people, that they use problems like this when they want to get out of work. When their mom or dad says, why don't you rake the leaves or take out the garbage or clean your room? I'd love to, Dad. I'd love to, Mom, but I'm working on this serious algebra problem. And, of course, it could take you half an hour to do it. And parents are certainly not going to require you to do work as opposed to doing your algebra homework. So it's always a good thing to have laying around. And I guess adults can use it when husbands and wives ask one another to do certain tasks, you know, turn off the TV. I can't. I'm too busy doing the algebra problem. Okay. Anyway, if we look and we select A and B as our first two numbers, we simply add 1 to B plus 1, divided by A, and B plus 1 over A is our third number. We add 1 to B plus 1 over A, and now we're getting a little complex, and divide by B, and we get the algebraic fraction A plus B plus 1 divided by AB. We take that fraction, add 1 to it, and divide that by the previous number, B plus 1 over A, and we get an even more complicated algebraic fraction, AB plus A plus B plus 1 divided by B squared plus B. And you're saying, look, these things are getting more complicated. How can we possibly get back to what we started with, which was A? Well, we take that and add 1 to it and divide by that previous, the fourth number, which was that fairly complicated fraction. And trust me on this, I mean, I do know mathematics. If you don't believe me, take out the old pencil and work it out. You wind up with A. No matter what A and B are. Obviously, A couldn't be 0 because then you'd be dividing by 0. But otherwise, any fraction, whole number, large, small, whatever you like, this says that for any A and B, when you do this process, the sixth number in the process will be A. And once you get back to A, then it's just A and B, etc. So, in reality, there is no trick, there is no magic, there is simply algebra as a generalization of arithmetic which allows us to look at why things work. You say, now, is that the only reason we learn algebra? The only reason we learn polynomials so we can check arithmetic? That sounds pretty silly. Well, of course it would be. It's just interesting that algebra is a generalization. Because, you see, we do use polynomials. We use polynomials as models to represent real-world situations. And we're going to look at this. In Lecture 8, we spend a good deal of the lecture looking at polynomial equations whose graphs allow us to approximate real-world relationships so we can predict what's going to happen if we can predict the future. We'll look at specifically quadratic and cubic models. Quadratic meaning they involve x squared as the highest power, degree 2. And cubics, obviously the highest power is x cubed, which would be third degree equations. Our understanding of these models allows us to truly work with the models in terms of, for example, doing things on a computer. You'll be able not only to understand what's happening, but also find errors. Now, some people would say computers never make errors. Obviously, those people do not get bank statements because I have seen computer errors. And I think it's very, very important that you understand what is going on. And these models are quite vital. But you might say, wait a second. We're going to talk about quadratic models. We're going to talk about cubic models. How about x to the 1 power models? Well, those are called linear models, and those are probably the most important models. And that's what we'll be talking about in the next lecture, which is Lecture 7. Linear models and linear equations, and using them to represent real-world situations that are very common, very important, and in fact they're so important we spend a great deal of time in high school and even college mathematics. So our next lecture, Lecture 7, linear models, you be there.